So I'm Brian Lindauer. I'm going to talk to you about the Human Computer Decision Systems line project. This is a collaboration with some other people in the SEI, as well as Jaime Carbonell and his group in the Language Technologies Institute on campus. So this project is about the situation where you've got a stream of information that you're trying to process, where you may want to apply machine learning, but the machine learning capabilities are not flexible, adaptable, sensitive to context in the way that humans are. Humans, of course, can't scale up. We can't hire enough analysts to keep up with this fire hose of data in a lot of these different contexts. So to be concrete about the kind of task that I'm talking about here, let's think about the CERT artifact catalog, which is a catalog of binaries that CERT collects in order to study and analyze malware for our stakeholders. If you look at the growth of this catalog over time, it's got this exponential or power curve type behavior. Staffing for hiring and employing and putting reverse engineers on this problem to reverse engineer all of that malware obviously cannot grow at that same rate. So the group working on that has looked at machine learning solutions to sort of take a first crack at classifying different families of malware from looking at the different features of these binary files. This is a point solution. What we'd really like to do is, in these kinds of situations, be able to develop solutions that can adapt over time and work with these teams of human analysts to really optimally use their limited capacity to provide, in this case, reverse engineering, but in general, labeling of samples of data coming in. So other places where you might see this are like security operations centers or incident response teams where you've got sensor data coming in that may pass through automated components like machine learning components. And you're trying to triage those and figure out which things to put analysts on first. Also, in the insider threat domain, you see applications of machine learning and anomaly detection there, whereas traditionally kind of a human counterintelligence task. But how do you work with these machine learning components and human experts together in order to optimize this overall system? So, give you a little background on where we're going with this, or sort of for you to understand what our improvements are, I got to give you a little background on what we're improving upon. So, in traditional machine learning, which I think probably most people here are most familiar with, you've got a bunch of data, and you've got labels on that data. These things are benign and these things are malicious, say. And you take a random sample and train up a model using your random sample and then test it using the remainder. There's a field of machine learning research called active learning. In that case, you've got a whole bunch of unlabeled data. With that unlabeled data, you're trying to choose the ideal sequence of samples to have your experts label so that you can get as accurate as possible of a classification of the remaining data. This active learning research in general makes some very unrealistic assumptions about the environment where you're working. So it assumes, for example, that the people providing these labels are sort of a singular oracle that always gives you the right answer. It's one entity, and that it's constant over time. When in fact, if we look around at the cybersecurity operational context, what we see is, teams of analysts. In the example I just gave, a team of malware reverse engineers of differing levels of ability, like Rotem was saying, you've got your A students and your B students. And they change over time. Additionally, the environment is not something that we completely control. It's an adversarial environment. The things that you're trying to label themselves are shifting from underneath you. So how do you keep up with that, and how do you make sure that you're optimizing not just the the construction of this machine learning model for the environment, but also the performance of this overall system of the people and the machine learning model and that combined team. So this is kind of the traditional active learning picture. You've got one class of things, these blue dots, and you've got these red triangles, and the yellow line is sort of how what you've decided your optimal decision boundary is for the moment. The current sort of mainstream way to do this is to, there's several different heuristics, but one is to look at the most uncertain point that you haven't labeled yet and give that to your analyst and say, tell me what this one is and let me improve my performance along that boundary. If you just look at how that performs against a random sampling of samples and getting labels on those, already you can see you get somewhat of an improvement. However, we'd like to take that further and actually, take into account these other aspects of a team of experts together with a machine learning component that are not being considered in the current research. So this is the two things, sort of two additional steps that are being taken beyond active learning here are what's called proactive learning, and that's where we assume that this oracle is not perfect or perfectly reliable, and that it's not singular. And then the human-computer collaboration aspect, where we consider this as a team of analysts and not just a single analyst. The classifiers the classifier's performance that's changing over time, as well as the analysts themselves have performance that's changing over time. So today, this type of research is mostly done using simulations, like the plot that I just showed you, where you develop your improvement to your active learning model, and then you run it through some simulations and say, okay, look, the error rate goes down faster as I select more optimal points to get labeled. But we know from what we've heard yesterday and today that we really need to consider the interaction of the human element in this process. And it's difficult to sort of realistically simulate that human element. So what we've been working on is actually running human subject experiments to study the combined performance of these active learning components with human analysts. In order to do that, in order to build an environment where you could actually test the improvements, we need three things. One, we need realistic data. So at least to the extent that class and feature distributions are similar to a domain where this can actually have an impact for our stakeholders. Two, you need human participants so that we see the actual patterns of errors and performance, and it's not just our own idea of what a simulated human should look like. And we need ground truth, because we can't trust that in a human subject experiment all of the labels that we get are true. Part of what we're looking at is, are we correctly predicting whether giving this person this object to label will result in a good label or a bad label. So we've taken this project on two parallel tracks. One is advancing the learning theory to account for these persistent human expert teams. So that's sort of the mathematical part of things. And then there's the second track, which is building the apparatus for these human subject experiments to validate those improvements and to validate future improvements to cybersecurity systems that use these machine learning components together with teams of human analysts. So again, here's the picture of the standard active learning technique, where you have some heuristic for choosing the next point. What we're doing instead here is looking at the team of analysts and trying to, I'm not going to walk through all of this, but basically choose the point that gives us the maximum estimated utility for the next labeling of the point. So we're doing that in the context of sort of a constrained budget. So you've got a team of analysts, they have different costs, and we have to work within that budget. So to get there, we've built sort of a framework that we're calling dynamic proactive learning. And as in the situation that I just showed with the sort of traditional active learning, we had one strategy. The one that I showed you was choose the most uncertain point. Other strategies are sort of choose the point that's got the most density around it of things that you don't know about yet. Well, what's the weirdest thing that we see right now that's got other weird things around it? What we're doing here is creating a framework where we can use multiple of these strategies at the same time, possibly very many of them, and including, the interesting part is this includes strategies that take the analyst into account. So whereas the classic strategies that you might choose from have to do with, how can I best, most benefit this machine learning model over here, and how can I reduce its error rate? What we really want as a, operational cybersecurity group is to have the best error rate of this combined machine learning and human analyst system. And so we're trying to optimize for that overall system, and this gives us a place to stick sort of the criteria that have to do with both the humans and the machine learning model, and combine those and update those weights dynamically over time. So I've been bad-mouthing simulations, but just to show you, that there is, even in simulation, an advantage to doing a dynamic weighting of just two very simple strategies of the uncertainty sampling and the density sampling that I mentioned. What you're seeing here, cost going across the bottom, is the number of samples that you've gotten labels for. If you assume, it costs you $1 to label each one. As you spend more resources to put analysts labeling these things, your error rate of your model goes down, and if you update those dynamic weights as you go, your error rate converges more quickly. So the other part of this that we're working on is this apparatus for testing these things and actually finding out whether these improvements, these improvements to the math really yield improvements to an overall system that includes humans. So to do this, we needed to create a learnable task, something that people could perform without being, say, expert malware reverse engineers or network security analysts. So to stay close enough to the real data that we could have confidence that the results would map back onto that real task as we transition this into the context that could really benefit people, on the front lines. We took some open malware data and mapped that using PCA down into a three-dimensional space and used that to generate stick figures that we're asking people to classify into the different families that correspond to families of malware that they came from. We built several software components to support this. One is an API that implements all of these proactive learning improvements that we were talking about. This is kind of a standalone component that could be plugged into other systems. Like as Rotem was talking, I was thinking, we could, as one sort of future step, plug this component into his system. That sits behind a server that manages these human subject experiments. We're doing those using Amazon Mechanical Turk. The reasoning there is that we don't have the resources to kind of take actual malware reverse engineers, say, or network security analysts, and with each iteration of this work, ask them, stop what you're doing, go try this experimental system and see if it works. So part of what we're trying to do here is create a task and an environment to test that task where we can sort of figure out the efficacy of this without needing to go through real security analysts. So we're doing this up on Mechanical Turk. Here's to give you a sort of view of what the task looks like. You've got a screen where you get shown one picture of one of these stick figures, and you're asked to label it into one of these categories. As you go along, the accuracy is tracked on the right there, so this is what a subject performing one of these experimental trials would see. So what we're looking at now is whether that task is learnable. That we've had to make some changes to it. The early results are that it's too difficult for sort of general public type people to classify these into different groups. And so we're trying to make it create a little more separation, because the idea here is not that the focus of it should not be that task. It should be testing the active learning improvements that are the focus of the task. Following that, we're going to be testing this dynamic proactive learning algorithm versus the baseline active learning algorithm, and adding in optimization components for the analyst versus classifier objectives. There's a few other things that we have in mind, sort of extending that experimentation framework to allow multi-session, persistent activities. Towards the end of the fiscal year, we're looking at testing transferability of results to an actual task, such as the malware reverse engineering task, or perhaps other cybersecurity operational tasks. So sort of the takeaway here is in looking at these problems, you really need to include humans in the system and take into account these humans in the system for the, if for nothing else than because we need to be resilient against an adversarial system. We should be, in contrast to the traditional active learning, we should really be optimizing for the overall performance of the system, the analysts and these machine learning components together. And we need an apparatus to develop those techniques and to test those techniques that goes beyond, or that lets us do that for, without taking the resources of actual security analysts. I'll just finish with a reference to this National Science Foundation funded report, the Cybersecurity Experimentation of the Future report, which they say in that report, one of their sort of like top 5 conclusions has to do with the ability to accurately represent humans in experiments and to instrument laboratory environments to get realistic views of human behavior. And that's really what we're trying to bring into the active learning research here, and to bring that research up to the point that it can be applied to the operational tasks that matter to us and the DoD and our other stakeholders.